Oh, can I start? So, hi everyone, I'm Jesus. I work on Polygon on the protocol team, and today I will explain an overview of the AggLayer, what we have currently on mainnet, and what we want to aim to do in the future. And it works. So first, a quick introduction in case that you don't know. What's AggLayer? AggLayer, we can say that's an interoperability protocol to coordinate chain settlement. So using zero-knowledge proofs. So basically, what we are doing is like try to coordinate the settlement of a lot of chains. And how we do that is like we try to we let the chain operators to define the chain security level that they want. But we always require a minimum, which we call it pessimistic proof, that I will go afterwards. And basically, what it does, the pessimistic proof, is basically try to keep the assets from one chain, like don't let other chains rug pull yours, right? So I will go there afterwards, but more or less it's a settlement layer. And all the chains share the same bridge interface, and this makes very easy to prove to prove these bridge interactions, and for instance, to make this pessimistic proof. So how we do it? We have all the same bridge, as I said, all the same bridge interface. We do this zero-knowledge proof that it's the minimum thing that we need to prove in order to protect all the chains, and the AggLayer node, which basically it's a server, it's a service that coordinates all this settlement and send proofs to layer 1. So I will explain a little bit more of the pessimistic proof. As I say, the pessimistic proof is the common proof for all the AggLayer chains. So basically, it's the minimum security guarantee. So all chains, in order to be in the AggLayer, needs to verify this. And basically, this is a chain accounting. So what is the pessimistic proof is basically checks the current balance of the chain, checks what are the new assets that the user sends to this chain, and what assets this chain sends to other chains. And basically computes the balance, and the balance should be always positive or 0, right? And if the balance is negative, then the proof fails, and basically this chain cannot settle in the AggLayer. And this is like the minimum, right? With this, you know for sure that all the chains cannot rug pull other chains. So you know that if you are on a chain inside of the AggLayer as a user, and you trust this chain because it has, I will explain, but it has some security properties. If there are other chains in the AggLayer that are less secure, it does not affect you as a user, which is one important property that we want to keep. And also inside of the pessimistic proof, we verify an arbitrary proof that we call it AggChain proof, which is defined by the chain operator, can be anything, and we are verifying it doing a ZKVM proof. And how it works basically is like the chain operator can define whatever state transition function that they want to put. Maybe can be an ACDCA or can be a full execution proof. So just a proof of all a trace execution of get, for example, whatever. And of course, depending on whatever the operator chooses, the chain will have more or less security guarantees. But as I said, as a user, you will choose, right? If you go to a chain which has full execution proof, you know that you will be secure because you trust get or reth. If you go to a chain that is just an ACDCA, then or a proof of stake or a proof of multiple signatures, then you know that your security will be less. But all the chains can benefit from being inside of the AggLayer, having this same bridge interface and having quick interactions. But of course, any chains will have different properties. Maybe the less secure ones will be cheaper, and the more secure ones usually will be expensive or slower. Okay, so this is like our last schema, and this is how Katana works. I don't know if you heard about Katana, but we deployed a new chain like some weeks ago, and I think today or yesterday the announcement that it's publicly launched. And this is how it works. As you see, we have what we have to the left thing, to the left side, is the AggChain proof, which basically is divided into 2 proofs. You will be used to that, but we verify a lot of proofs inside of proof because we are on the recursion era, and everything is verifiable. So you basically split whatever the logic you want in proofs, and you verify all of them, and it works. So inside of the AggChain proof of the system that we have now, we have the OP succinct proof, which basically we run our OP nodes, we verify them using a library that succinct did, using succinct technology, SP1. And with this, we have a proof of OP. Then we took this proof of OP and we get the state roots of these proofs, of this chain. And we check the layer 2 storage of the bridge. And basically match all the layer 2 storage. Basically, we check everything that happens in the bridge, in the storage, and say, OK, the users send these assets to this chain and claim these assets from this chain. So basically, we check what assets this chain received and what assets this chain sent. And we match this with the pessimistic proof. So basically, what we are seeing here, like we have the minimum security guarantee, which is the pessimistic proof, that is the chain level accounting, and the AggChain proof is like adding security, both having a full execution proof and then matching this full execution proof state with the pessimistic state. And finally, after this AggChain proof is generated, it's verified inside the pessimistic proof alongside the other logic that I said, and finally on the layer 1. Okay. Okay, now this is a flow on what's actually how the information flows from the layer 1 perspective. So how it works on layer 1 is like we have a layer 1 contract that's called rollup manager, and basically it manages all the chains on layer 1. So anytime you want to be added inside of the AggLayer, you create a new contract, which is called, I call it AggChain smart contract, a consensus or AggChain contract, and there you put all the logic that you want that it's extra, right? All these AggChain proof parameters that I say that are alongside the minimum logic. And how it works is like, okay, you create a network, you create your own AggChain smart contract, and you attach it to the AggLayer. And when AggLayer tries to settle a proof, it will get the information from your smart contract, and it will get your aggregation B key and the AggChain parameters. The aggregation B key, I don't know if you're used to the ZK VMs, but basically defines the program that you want to verify. So defines all the logic that your chain has alongside the minimum, which is the chain level accounting, which in the case that we just see, it was an OP succinct proof. And the AggChain parameters will be the parameters that you want to check from your proof to the layer 1. So for example, if you are verifying an OP succinct, probably you will want to check the previous state root or the previous block number. So you get some information from layer 1, which is there, and the AggChain parameters. You choose whatever logic you want, in this case, full execution proof. And then this is retrieved on layer 1. So as a user, you are sure that once a layer is attached to the AggLayer, you know which security guarantees has. You know if it's a full execution proof, you know if it's a CDCA, or you know if it doesn't have more security guarantees and they just are pessimistic proof. So I will do a quick flow now. Here we have the user that sends a transaction to the sequencer, and basically this updates the OP node state, right? Then we have a module that is called a kit, which basically is the module that is in the middle of basically the rollups stack and the AggLayer. This kit, for example, in this case, it will have somehow a module that it will be a rollup prover, which basically will generate the proofs of this OP succinct with Kona, with this library, and also with synchronize the bridge of this chain. And with these informations, I can generate the proof that I showed you before, that it was the OP succinct plus the bridge proof, and we'll send what we call a certificate. In the AggLayer, any chain that wants to do a state transition, so it wants to update their state, it has to send a certificate. It's like the transactions or the way to say the AggLayer that you want to update your state transition. And basically, the kit, what we will do is like fetch the information of the rollup stack, generate the proofs, have to generate some proofs of the AggChain, in this case OP succinct, and send all of this to the AggLayer, with all the proofs computed. Then the AggLayer will check the proofs, check that everything is okay, and will accept the certificate. And then basically, the state will be settled on the AggLayer, and afterwards, the AggLayer can send this certificate or a lot of certificates to layer 1, depending if you aggregate the proofs or not. And this is the same data flow, but a little bit more like expanded. I just did like a minimal one, and this is on our docs. And if you want, you can check it. Like it's the same thing, but it's bigger. And it's just a quick reminder that you can check it on the docs. And okay, now that I explained like a little bit of introduction of everything, now I want to share what actually is on mainnet. So what I explained is like our new system, but not all chains use that, because basically we are operating with a lot of chains and a lot of legacy chains, and it's very difficult to update them all at once. So this is the current status of this morning of the AggLayer. As you see, this is Cardano and mainnet, and basically we have a lot of Validiums or GKVMs that use the Hermes prover. In case that you don't know, before having the AggLayer, we make an EVM Hermes prover, which basically was a ZKVM. And most of the chains are these legacy ones that they don't use PP and all these systems, but they are just plain EVMs. And anytime more, and the plan is to upgrade all the chains to this system. We want to upgrade the chains to the PP, which is the next generation, which is the pessimistic proof that I just talked about. And the last thing that we did is the AggLayer gateway chains, which basically is a PP, but also has this AggChain proof that I talk about. And as you see, we have two right now, which is Bokuto and Katana. And Bokuto is the testnet of Katana, which is the new chain that has this full execution proof with OP succinct and everything. And as you see, this is the current state. So we have a lot of legacy things that we want to migrate. We have this new system that seems to work. The AggLayer basically coordinates all the certificates of all the networks and submits the transactions to the chain settlement. And currently, we are using only SP1 to verify all the proofs. And this is related to the future state, which the point will be to have more than one ZKVM to verify the proofs. So to both AggChain proofs and the pessimistic, the idea will be to have multiple ZKVMs. And in this way, you can have more security. For example, following the approach of the Beam chain, where you can be protected about soundness issues if you have more than one prover that can prove the same thing. So you can have redundancy here, or you can make a cost efficiency games because these provers are advancing very fast, and each day one is more efficient than another. So the best way will be like to be able to verify everything with everything, and choose in the last moment which one is the most optimal one, right? So this is one of the points. Other thing is the proof aggregation. Even if something super easy, we didn't focus on aggregate these pessimistic proofs, and this is like something that we want to do now. As you see before, we don't have much pessimistic chains yet, so it was not a priority, but now it will be, because now we are starting to have more chains, so it's something that it's very doable and we have shortly. And finally, we want to focus on pre-confirmations, which this will allow this fast secure bridging between chains. Like reusing this logic where you have the same bridge interface and you have all this settlement layer, you can use that to have fast pre-confirmations between chains and to have fast bridging that probably you heard about it. And that's it. I have, if you want, I can show you a dashboard, or well, what I showed you before, which is this. Which is the current dashboard. I know, it's not showing. It's not working. Espera. Just if I don't put whole screen, it works. But if I click here, the link will be leaked. Let's do it quickly. Vale. So the URL cannot be filtered yet, I guess, because they told me to not do it. So forget about the link. And this is the current dashboard, which is fetching just information from the layer one, basically, and Sepolia, and it's fetching like all the rollup information as I showed you before. And this, for example, is Katana, and here's how it was deployed, and it was updated to AggLayer gateway to support OP succinct. And these are the certificates that I'll talk about, which basically this is a proof from the some block to some block. And finally, we see that we have some activity today because I guess it's the launch, so the people they are working with. I guess that they are playing with it. And now, yes, I finish. Thank you so much for assisting the presentation. pude preparármela mejor.
Do you have any question? No question? Okay, thank you very much. Oh, one.
My question is quite generic. If you're kind of creating transaction across different chains, and it's need to happen like in sequence, what happens if transaction is finished on one network, but didn't finish on another one? So that kind of the full transaction is not finalized.
So you're talking about super transactions, maybe? Yes.
But as understood, like it's about because you're doing with the ZK proof, obviously there is no transaction here. It's only the proof of transaction itself. But my question is that if the transaction is quite complex and goes across different networks, like how to coordinate that?
Our current approach is it will be multiple transactions. So each time these transactions go to a different network, it will be a different transaction. So it can revert in any time of the play. So imagine I am on Katana, I'm on one chain, I want to do a swap on another chain. Probably what I will do is like first interaction to this Katana, this other chain, this Uniswap. Then another transaction will happen on the other chain. And depending on the results, the funds might return in one way or another, right? So my transaction will always go through, but then I will handle the logic in the next transaction of the next chain. Does this answer your question?
Yeah.
So we don't have this where we block the state and we make a transaction which goes through.
Yes. So I just was curious how you're addressing that particular situation. So you're kind of dealing with the state already, like after, right? So
Exactly.
And if there was, for some reason, transaction didn't finish, so it means previous steps already finished. I mean, so you cannot return them.
Yeah, so you can return it in application level, not in ZK level. So your transaction will revert, but maybe you can have a smart contract and say, okay, if this reverts, just return the funds to the user, and that's it.
Okay.
And if it's fast enough, it should not have much collision if you do it on application level, I think.
Okay, clear. Thank you.
Thank you. Any question? Other question? Thank you very much.
Thank you.